All right, so in this video, we're going to talk about how to find roots, also called zeros, of polynomial functions. So this is just basically if you were setting a polynomial equal to 0, trying to find what values of x make this thing equal to 0. And this is going to be a 2 or 3 part discussion here because, as you are probably aware, unlike quadratic equations, if I didn't have that x cubed term there, we have ways of solving that, right? We could either factor it, maybe use the quadratic formula, but as soon as the equation gets degree 3 or higher, we don't have too many techniques at our disposal to use. But I do want to remind you on this first one that if you have a polynomial with 4 terms usually, one thing you can try to factor this is factor by grouping. Remember this, it's a skill you've for sure seen in an algebra class. And the idea is if you group the first 2 terms and the second 2 terms, so parentheses here. Now, if I put parentheses around the next 2 terms and take that minus out, I do have to remember that if I take that minus out, this is going to turn into a minus 12. And in the first set of parentheses, I can take out an x squared. That leaves me with x minus 3. In the second set, I can take out a 4, which also leaves me with x minus 3. And then I see between these 2 terms, I have a common factor of x minus 3. So I can factor out x minus 3, leaving me with x squared minus 4. I'm just using brackets because I have a lot of parentheses already, which happens to factor again. That's a difference of squares, x plus 2, x minus 2. And then I can use my zero product property. I know that if x minus 3 is a factor equal to 0, I know one answer is positive 3. From this factor, negative 2 is a solution, and positive 2 from my third factor. Okay, so remember, this is an option. Again, we call this factoring by grouping. Factor by grouping. Now, obviously, this wouldn't work. It was just the way the problem was set up when we factored out that we had this common factor of x minus 3 that we were able to pull out. If I had taken out a number here and these factors were different, this would not have worked. I would not be able to do that. So it's not a very, it's useful to know that, but probably most of the time you will not be able to solve these by grouping your terms. For example, my next one here, hopefully you can see if I group the first 2 and the second 2 terms, this is just x plus 6. I can't do much with that. But even if I factored out an x squared, I would not end up with x plus 6. I'm not going to be able to factor this one by grouping. So what else we could do is now this one, the problem gave us a hint, is notice that if they told us that f of 2 is equal to 0, and we can confirm that if you plug in 2 for all of those x's, you should be able to see that that's equal to 0. What does that tell me? It tells me one of the factors. If f of 2 is equal to 0, think backwards here, right? That's how we got those zeros. A factor must have been it must have come from a factor of x minus 2, right? Because that's when we set it equal to 0, that's how you would have gotten positive 2 as the number that makes it equal to 0. So then what we could reason then is that this cubic polynomial, I'm going to go ahead and write it out, factors into x minus 2 times something, right? We want to know the rest of the factors. We know one of them. So how would I find this remaining term here? Well, I could just divide both sides by x minus 2 to isolate it. So to find the remaining part, the remaining factors of this cubic, I need to do the division of this cubic with x minus 2. On the previous video, we've talked about lots of ways you can do the division. You can do polynomial long division. This one would work out pretty nicely with synthetic division. Recall, if I want to divide this by x minus 2, then I'm going to have 2. I'm going to write my coefficients, 1, negative 4, 1, 6. Bring down the 1. 2 times 1 is 2. Negative 4 plus 2 is negative 2. 2 times negative 2 is negative 4. Add those together, I get negative 3. 2 times negative 3 is negative 6, and that gives me a remainder of 0, which means, of course, that 2 must have been a factor, but we already knew that. But more importantly, what it tells us is the remaining factor here must be x squared minus 2x minus 3, which that's just a regular old quadratic, which we know happens to factor into minus 3 plus 1. And so we have this thing completely factored. So therefore we know our original polynomial factors into, remember we had that x minus 2. And what we did when we divided it was just to find the remaining polynomial, which was a quadratic, which we then factored into x minus 3 times x plus 1. So if I was setting this equal to 0, it's easy to see now that my solutions would be 2, 3, and negative 1. Let's do one more. Here's a 4th degree polynomial now. Has 5 terms, so probably not going to try the grouping thing. But again, they gave us this hint. If we called this g of x, they told us that g of 1 is equal to 0, which means we know a factor has to be x minus 1. Okay. And so from the previous example, we can see what I'm going to have to do to, I know a factor is x minus 1, but there's going to be more stuff. I'm going to have to divide, right, to figure out, we call this the reduced polynomial. So if I divide this factor, now divide polynomial by x minus 1 to get what we call the reduced polynomial. So, and I might as well do synthetic division since it's fast and easy. So I'm going to divide 1 into 1 minus 2 minus 3, 8 minus 4. We better get 0 or they lied to us here, huh? So bring down the 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. 1 times negative 1 is negative 1. These add up to negative 4. 1 times negative 4 is negative 4. Those add up to positive 4. 1 times 4 gives me positive 4, which gives me a remainder of 0 as expected. So my reduced polynomial, what is also a factor of this is now 1x cubed minus 1x squared minus 4x plus 4. So I could write this polynomial as x minus 1 times this, but I'm still going to have to try to find out where this is equal to 0. So we just treat it like a new problem. Let's see if we could figure out where this would equal 0. And now notice it's a cubic and I have 4 terms, and you may notice that you could probably factor this by grouping here, huh? If I separated out the first 2 terms and the second 2 terms, so if I do that, I'm going to pull out this minus, and that's going to leave me with 4x minus 4, because the negative times the negative would be that positive. Take out an x squared, I'm left with x minus 1. Take out a 4 there, I'm also left with x minus 1. So then x minus 1 can be factored out, leaving me with x squared minus 4. Go a little too fast to keep up with my video here, which I know factors again into x minus 1 times x plus 2 times x minus 2. Okay, so going all the way back, remember our first factor that we knew was a factor was x minus 1. So that in addition to these three, so we can now say our polynomial, I'm just going to write g of x since that was our original polynomial, was our original x minus 1 times all of these. You could, of course, write this as x minus 1 squared times x plus 2, x minus 2. And if I was setting this equal to 0, I can see that I'm going to have answers at 1, -2, +2. Now the question, this is going to be answered in the next video. We were able to work that out and reduce the polynomial, but it was kind of nice that they gave us this hint, which is essentially telling us one of the factors of our polynomial. What if they didn't give us that hint? How would we have figured that out? I mean, obviously we could have just tried numbers and plugged it in, and you know, 1 is a pretty logical number to start with. And if you plugged in 1 for all those x's, you would have seen that you would have gotten 0, right? So then you would have known that was a factor. But what if 1 wasn't a solution? What if it was something bigger than 1 that was a root of this polynomial? How would we have known? So on the next video, we're going to talk about how do you, from the look of a polynomial, how do you come up with numbers that would end up being factors, would end up being roots of this polynomial? So we'll discuss that on the next video.